This slideshow will be on multiple dosage regimens, including multiple administrations of a drug, but then also IV infusion. Even though IV infusion is not really multiple administrations or multiple dosages, we can treat it in a similar way, because if you break up an IV infusion into kind of small time points or small doses, it pretty much functions the same way as a standard multiple dosage regimen when it comes to the calculations. The learning objectives are to explain the principles of superposition and its assumptions in multiple dose regimens, explain why drugs reach steady state rather than accumulating to toxicity every time we have repeat dosing, and that's related to the question that I asked at the end of the oral pharmacokinetics lecture. Explain the 5 half-life rule regarding steady state, describe the Cmax and Cmin. Describe what they are. Of course, we already talked about Cmax, but now we're going to include Cmin. So understand what those are and how they may be changed without changing the average steady state concentration in a multi-dose regimen. Calculate the steady state Cmax and Cmin after multiple IV bolus doses of a drug. Calculate the plasma concentration at a given time with multiple IV bolus doses of a drug. Calculate the steady state concentration with continuous IV infusion. Define loading dose, its main purpose, and how, if it relates to the steady state concentration of a drug. Just starting off with a basic introduction. In reality, most drugs are given in multi-dose regimens. Multi-dose regimens are designed to keep the drug concentration within the therapeutic window, which means above the minimum effective concentration and below the minimum toxic concentration. Right? So that's implying, of course, the drug concentration will fluctuate, but we want to keep it in a certain range. The two main parameters that can be adjusted in a multi-dose regimen, of course, are the mass of drug taken, which is the dose, and the frequency of administration, which is the time interval, also called tau, which is the Greek symbol tau there, as you can see. So keep that in mind. The tau means how frequently we're going to administer the drug. So we're going to talk about drug accumulation in multiple dosing now. We can use data from a single dose regimen to estimate the appropriate dose and frequency in order to achieve, first of all, a desired steady state concentration in a desired Cmax and Cmin. That means I can give a single dose of a drug to a study population, and based on the measurements I get from that single dose, I can make good predictions about what will happen in a multiple dose study. Okay, so that allows us to choose dosing for a multiple dose study. The general assumption is that the previous doses of the drug do not affect the pharmacokinetics of subsequent doses. That means if you give a repeated dose to someone, any drug remaining in the body, the assumption is that that drug there does not have an influence on the pharmacokinetics of the new drug, the new dose of the drug that you're adding to the body. And that is called superposition. Okay, so the new dose area under the curve will superimpose itself on the previous dose area under the curve. So whatever's remaining in the plasma from the previous dose, it's actually just it's really just additive. The area under the curve at least is additive. We still have our standard constants involved, but the AUC is additive. There are cases where this is wrong. Of course, if you give some drugs multiple times, you may change the pharmacokinetics of that drug because you may induce an enzyme that metabolizes it. You may affect the transporter. There's a lot of things that can happen. So from time to time, we have drugs that do have changing pharmacokinetics based on repeated dosing. So I guess I just answered this question about what do you think might cause a drug to have changing pharmacokinetics after repeated administration. Again, that could be changes in drug metabolism over time, induction or inhibition of an enzyme is a common example. So remember how constants are supposed to be constant except for when you have a strange scenario where a drug is inducing an enzyme and then the KEL might actually be higher over time, right? So that can change in some instances. So I don't want you to kind of be able to do this, so you don't have to repeat this on a test or anything like that. But this is to give you an example of what superposition would look like. So if we gave, if we gave one dose and we watched the plasma concentration over time, okay, and that's what this is. See this plasma concentration up top, and that's what these are. So we give dose 1, and the plasma concentration, like right before you give it, is 0, and then it goes up a little right during absorption, and then it goes back down. And if we just watch that one dose, we plot this or put this on a table, and then we give. So that's all in one experiment, just one time we watch one dose. And then we can predict what would happen if we gave another dose. We'll say just for instance at 4 hours, which is what this example is. We give another dose at 4 hours. You're just adding. If you look up here, the first dose gave us a plasma concentration of 21 at 1 hour. So the second dose would contribute also 21 at 1 hour. But if you add that to what would have been remaining from the first dose, then it gives you a higher total concentration. So the predicted concentration will be 35.3. And you're adding, all you're doing here is adding the second dose to the first dose. So if you look, these numbers are the same: 21, 22, 19.8, 16.9. All you're doing is shifting them into the second dose, and you're just adding them together with whatever would have been residual from the first one. And then you're doing so on and so forth. Dose 3, again, the first, right, every hour is going to give you the same plasma concentration, just the contribution from dose 3, but then you have to add the contribution from dose 2 and dose 1, and then it gives you a higher concentration when you're adding them. So that's the superposition idea, that it's just additive, right? The contribution of a dose to the plasma concentration is additive in many cases, right? Unless there's some abnormal or strange phenomenon where you're changing the enzyme activity levels or something like that, which of course that can happen, where you raise the dose, or you raise the concentration, and you start to induce an enzyme, and then you metabolize faster, and then you can't use superposition. But in many cases, this is actually reliable. So we talked about area under the curve for single dose regimens, for example, like IV bolus. What about area under the curve for a multi-dose regimen? One of the things that, I don't know, it might be a little surprising to you, at least to some of you, is that if you take, for example, just a single dose and you watch its plasma concentration and you measure the area under that curve, believe it or not, that will be the same as the area under any interval. If you repeat the same dose over and over again, that interval between any two doses, the area under that will be the same. So we'll look at the last one here. That area will be the same as the area under just the original single dose. Okay, so that's an interesting phenomenon that we can actually use that in some of our calculations if we wanted to, that knowledge. To me, one of the most interesting things in pharmacokinetics is that multi-dose drugs eventually reach steady state rather than accumulating more and more. So that's the question I raised in the last lecture. If you keep giving a dose before the drug is eliminated completely, why doesn't it, so first of all, does it accumulate forever, right? Just forever and ever and ever until it's toxic, or does it not? And actually, the answer is the vast majority of drugs do not accumulate forever. They will reach a steady state, even giving the same dose in the same frequency over and over and over again. Most drugs will reach a steady state, right, where the average concentration is not changing over time. So the only thing we will see is a max and a min, max min, and the max min will be the same. Once you reach steady state, all the C maxes will be the same, all the C minimum will be the same. Okay. And in this example, the same drug was given either every 6 hours or every 8 hours. And you can see if you give it every 6 hours, yeah, you'll get a higher steady state, but you'll still reach a steady state. If you give it every 8 hours, you'll reach a lower steady state, but you'll still get to the steady state. And one of the interesting phenomena here is that both of them reach steady state near the same time. You see this here? So where does it actually flatten out? Maybe approximately around like 70, approximately. So in this example, we're seeing that regardless of the dosing frequency, we're getting to steady state, or the point where the average is not changing. We're getting to there around the same time. Okay, so again, we're going to talk about that a lot more as we proceed through the lecture. So again, it's back to that question. Why do most drugs not continue to accumulate and eventually reach a toxic concentration in the blood when we repeat administration for weeks or months or years? Is it washed out of the system before we give it again? And obviously the answer we're seeing here is no, because we saw that in the last graph. It's not going down to 0 before the next dose. So is it something else? Okay, the answer is it is something else. Okay, and hopefully you've already tried to come up with a conclusion, or at least a hypothesis as to why the drug doesn't accumulate forever until it reaches toxicity every time, and in most cases it doesn't reach toxicity. So hopefully you can think about that, because we're going to talk about that as we proceed here. So actually, even before I talk about this slide, I'll answer that last question right now, and that's because remember, these drugs are mostly eliminated in a first order process. So as you raise the concentration by giving, so you can even see right here, if you raise the concentration by giving multiple doses, and the concentration is going up and up and up, remember, it's a constant percent removed per unit time. So if the concentration gets high enough that the percent removed ends up like basically removing the same mass as the dose. Think about that. So we're giving the same dose, same dose, same dose, same dose, same dose, same dose. But just say like any percent, like 10% of whatever this is would be more than 10% of whatever this is. So as we're going higher and higher, because it's removed by a certain percent per unit time in the elimination, we're actually removing a higher mass as the concentration gets higher, right? The body's removing a higher mass. So eventually that mass removed will equal the mass of the dose, and then we'll reach steady state. Okay, and the only reason why that is possible in the body is because our organ systems have not been saturated. That means not every hepatocyte is at full capacity in terms of the amount of drug it's metabolizing. Not every glomerulus or every tubule is at its maximum ability to remove drug or excrete drug. So that means there's capacity for more, right? So that means the vast majority of drugs are nowhere near saturating the elimination routes. So we still have, so if we double the concentration, we double the removal rate, right? And that's why eventually we reach steady state. Okay, so that means our doses are very small compared to our organs' ability to handle them. Okay. So now let's get back onto this slide here about steady state. Although steady state is reached in most cases with repeat administration, this does not mean the concentration is absolutely steady. It means the average concentration becomes steady. You see, it's going to bounce up and down, but eventually the average, or if we drew a line through the max and min, right, it would just be steady at, maybe 800 or something like that. So we reach an average value that doesn't really change much. So we still have a C max and a C min, right? And we have to keep these in the therapeutic window. And I just drew something that kind of looks like a window here to basically illustrate that the reason why they're calling it a therapeutic window is because it's basically a box. You can kind of draw a box within which you want to keep your a box or a window within which you want to keep your concentration. So you don't want your Cmax above it. You don't want your Cmin below it. And the therapeutic window means, above the bottom we have efficacy, above the top we have toxicity. So we want to stay in between those two. Okay, and to be honest, not every single drug has a window like that, because cancer drugs or anti-cancer drugs, they are usually, not all of them, but a lot of them are toxic at the therapeutic dose anyway, right? So it depends on the drug type, but the goal is to avoid toxicity and achieve efficacy in most cases, right? So really in all cases if we can. So more on steady state, since that's one of the most important things to consider when we're considering multi-dose regimens. So a phenomenon in pharmacokinetics that is, I think in most cases people do not find it intuitive, is the fact that the time to reach steady state is independent of the dose and the dosing interval. And this is very easy to confuse. So what it's saying is the time that it takes to reach steady state is independent of the dose and the dosing interval. That doesn't mean the steady state will be at the same concentration for every dose or dosing interval. It means how long it takes to reach steady state will be the same time regardless of the dose or dosing interval for any drug. So that's really surprising, maybe to some, at least it was to me when I learned about that. So if you double the dose and maintain the same dosing interval, so if you're giving it every 4 hours but you double the dose, it'll still take the same amount of time to reach steady state, right? So it's and that's, again, it's all based on the first order elimination process, that it takes the same amount of time for you to reach a concentration that, where the body's eliminating the same amount that you're adding every dosing interval. Okay, so the time to reach steady state is only dependent on the elimination half-life of the drug, which is directly related to the KEL. So it's the same idea. So the elimination half-life is the main determinant of how long it takes to reach steady state. Okay, so I already mentioned the third bullet. So the whole idea is that changing these two things does not change the time it takes to reach steady state. Okay, and I already mentioned this, I just want to emphasize it one more time. This does not mean the concentration will be the same for any dose or dosing interval. It just means the time is the same for steady state. So using the Excel calculator that I developed, I inserted two different situations, or two different dosing scenarios here again, this is multiple IV bolus doses. So I tried 125 milligrams every 4 hours, and then I tried 300 milligrams every 2 hours. So this has a lower dose and a less frequent administration. This is a higher dose and a more frequent administration. So this is giving a lot more drug on the right. So using our basically our IV bolus multidose equation, which I'll show you, we have an equation for this. Plugging everything into this equation, what I got was, and I had to add this, by the way, I had to add a half-life and a KEL. So I said, well, if it's the same drug, it's going to have the same half-life and the same KEL, which are both related to each other. I put the same volume distribution because it is the same drug, right? So that's a constant. Everything pretty much the same. And what I did was I plotted it, and what happened was, notice we get to steady state, and you have to, you have to estimate kind of where that is, but anywhere from 20 to 25, we'll say hours basically. Now look at the more frequent and higher dose. 20 to 25 hours was starting to get flat. Okay, but notice, so we do have some differences. The main difference is the concentration is much lower on the left because we're giving a lower dose and less frequently. The concentration, of course, is much higher on the right because we're giving a higher dose and more frequently. But notice one other difference is that the Cmax and the Cmin, now this scale is obviously different, but if we go by percent, like percent of whatever, 25, the Cmax and Cmin is jumping a lot more. Whereas if we're looking on the right here, the Cmax and Cmin, relative to the total concentration, that's not much of a percent. That's not as high of a percent variation as it is over here. And that's because our dosing frequency is more frequent. So the more frequently we dose a drug, the more steady we'll get it. So the Cmax and the Cmin will be closer to each other. So if we had a drug that had a really narrow therapeutic window and we wanted to avoid getting high Cmaxes, we could give it very frequently at a lower dose, or we could give like an IV infusion, so that's even better because it's constant. It's steady, right? There's no spiking up and down because you're infusing it constantly at a low volume per minute, or some volume per minute basically. So that leads us to continuous infusion. So a continuous infusion of a drug via IV administration can be thought of as like a gazillion tiny dosing intervals with small doses. And that's one of the ways I look at it. So it means that the IV infusion is giving a constant volume of drug solution through the intravenous route every minute. You're giving a constant volume. And because you're not giving it every hour, every 2 hours, you're giving it constantly for the most part, it's going to give you a nice smooth curve. But you can kind of break it up, if you wanted to break it up, into a gazillion mini doses, like every second or every half a second. You could do that if you wanted to. So the whole point is that the steady state, the whole point of the steady state being the same regardless of the dose, or I should say that the time to steady state is the same regardless of the dose and dosing interval. That holds true with IV infusion as well. So if you take a drug that used to be oral, or used to be, well, let's probably a better example. If you take a drug that was IV bolus every 4 hours, and then you switch to IV infusion, and you give the same dose, average dose every 4 hours, but you're infusing it constantly, the time to steady state will still be the same, right? Even though you're giving it, constantly through the infusion rather than every 4 hours. The big difference again is there's not going to be any Cmax or Cmin since the drug is constantly infused. So this is what it actually looks like when the equations that we'll talk about them. The equations are plotted with real data, or on a spreadsheet. You actually get kind of a nice plot like this. So what I'm showing is basically I can give 300 milligrams every 2 hours, and let's just assume for simplicity's sake that it's 100%, we'll just call it IV bolus, so it's 100% absorption, so it's IV bolus. 300 milligrams every 2 hours. Infusion dosing looks different because we have to know how much drug is dissolved in the infusion solution, how many milliliters per minute are administered, and then how many milligrams per hour does that equate to based on this concentration and infusion rate, how many milligrams per hour. So I'm saying it's the same drug, so it's the same volume of distribution, half-life, and KEL. But if you look at this, again, this is 150 milligrams, approximately 150 milligrams per hour. So every 2 hours, that would be 300 milligrams. That would be the same as basically like giving an IV bolus every 2 hours. So it would be, you basically be given the same mass every 2 hours, just a different rate, or I should say different method by giving that. So you're giving it constantly through an infusion rather than in a bolus dose. So if you give the bolus, you're going to see these spikes here. Okay. If you give it by infusion, you get no spikes. You get a constant flow into the blood. But guess what? The steady state, and again, we're going to have to estimate where it actually gets flat, right? Because it's still slightly going up. So it's I would say approximately around between 20 and 25 hours. If you look over here, it's almost the same. And as you can see, it's actually still going up a little bit at the end, and it kind of is here on these dots as well. So the whole point, though, is that the steady state time, right, does not change. The time to steady state is not changing regardless of the frequency or the dose, because it is the same drug, it is the same time. Now, obviously, if I increased the infusion rate to like double, then of course the concentration would approximately double, but it would still take the same amount of time to get to steady state. Okay, so those are the main points that I want you to understand from this. So for IV bolus multidose, we can actually calculate the plasma concentration at any time with the equation to the right. So Cp equals the dose over the volume of distribution. Okay, and because it is IV, we don't have to add the fraction absorbed here because that's 100%. And that's going to be times 1 minus e to the negative n kel tau. So the n is the number of doses given. Okay, and that so if you're going to do it like right after, so if you want to know like a second after the last IV bolus or a minute after the last IV bolus, you would still count that. You got to count that last dose. So remember the first dose is always at 0, right? First dose is at 0, right? And then the second dose is whatever your interval. So the second dose would be at 2 hours. Third dose would be at 4 hours in this example. So again, n is number of doses given so far. The KEL, of course, is the elimination rate constant. The tau is the frequency, so that would be every 2 hours, so that'd be 2. And and I'm not going to go through the whole equation, but at the end here we have t for time, and that is that's actually the time. Let's be careful here. That's the time after the nth dose. So if I say 10 doses, I want to know the plasma concentration immediately after 10 doses. Like immediately, so I'm saying like right after the 10th dose. I would put a 10 in where it says n, I'd put a 10 there, but the time after the nth dose, or the 10th dose in this case, would be basically 0. So I mean immediately after giving it, right? So you could put a 0 there or a very, very low number because we're saying right after that dose. So you're going to use also the elimination rate constant on the bottom of the equation, and again the tau, which is the frequency, again on the bottom of the equation. So this is really cool. So it's not a super complicated equation that will tell us the plasma concentration at any given time, right? Based on this predetermined data, though we'd have to have all of this ahead of time. Okay, so I want you to try this on your own using the same IV bolus dosing information from the previous slide. So that's all right here, right from the previous slide. And just to kind of start you guys off, why don't we just pick a time point? And I said 21 hours. So what if I said, what is the plasma concentration at 21 hours? Okay, you'd have to, the only thing you're going to really need to know is because you already have a lot of this data here, the plasma concentration at 21 hours, you'd have to know how many doses did we give, right? We already have the dosing interval, we already have the actual dose, the VD, but how many doses did we give at 21 hours? So again, you have to think about that. The first dose is at 0, right? Second dose is at 2, third dose is at 4, fourth dose is at 6, fifth dose is at 8, and so on and so forth. So it's a lot easier if you write this out, though. So, or you could do a simple multiplication. But the idea is how many doses are we at 21 hours, and that's what we're going to insert into the equation. So like I said, there was a dose at time 0. So at time 21, what dose did we give last? Okay, so if you continue with what I was doing there, you'd find you should have gotten to the 11th dose. So at 21 hours, we should have gotten to 11 doses, okay, have already been given. If we need to calculate the KEL, remember, the equation that we're talking about doesn't have the half-life in it, and actually has the KEL. So we may need to convert the half-life to get the KEL sometimes if someone only gave you the half-life. So remember, it's a simple equation. T1 half equals 0.693 over KEL. So we're going to manipulate that, and we're going to hopefully get a KEL of 0.1386 per hour. So what does that look like now, a step at a time? So I want you to pause it and finish using this whole equation to calculate that plasma concentration, again at 21 hours, and tell me, but basically see if you get the same thing that I get. So go ahead and pause it now. I'll give you 5 seconds and then I'll continue. Okay, so I'm going to go ahead and continue and reveal the work here. So just entering the numbers in, right? It might seem bad, but it's really not terrible. The only thing you had to do is figure out how many doses we gave, right? And that would be entered right at this n value here is number of doses. But the one thing that I didn't mention that, of course, you had to figure out as well is how long has it been since the last dose or the nth dose, right? The nth dose was the 11th dose. 21 hours is actually 1 hour more, or 1 hour after the 11th dose, right? 21 hours is 1 hour after the 11th dose, right? Because we had 11 doses exactly at 20 hours. So you can't just, right, you basically have to figure that out. You have to know what T to put or what time to put in there. Again, that's how much time has passed since the last dose. Okay, put that all in there, and hopefully get 91.88 milligrams per liter, which is again the same as micrograms per milliliter. Okay, and I think you'll see, go back to the graph, you'll see basically that we're approaching that number in the graph as well. So now I have a completely new problem using the same equation. This time we won't have the graphs, so you can't really guess at anything. So I wanted to see if you could just kind of from scratch come up with the answer. So we're starting off with a simple calculation just in the question here. 5 milliliters of an investigational drug. It's at 100 milligrams per milliliter, so that means it's in a solution. It's given every 8 hours via IV bolus. So first of all, you have to calculate what is the actual mass or dose given, every 8 hours. So obviously you're going to take the 5 milliliters and then multiply it by the 100 milligrams per milliliter and get 500 milligrams. So it's a 500 milligram dose every 8 hours via IV bolus. And then we have our VD and our T1 half. Okay, so what will the plasma concentration be immediately after the 10th dose? So this time we don't need to calculate what dose we're on because it's given in the equation or in the question, right? The dose is given right in the question. Remember before we had to figure it out because we're looking at a specific time point. So now we know we're going to be after the 10th dose, so that the 10 would go in the equation for the n. But then we have to decide what time after the nth dose we want to choose. So I said immediately. So you can actually safely go with 0 hours after the 10th dose in the equation. So go ahead and pause it. I'll give you 5 seconds right now. See if you can figure out what the concentration would be, and then we'll move on to the next question. Okay, I'm going to go ahead and reveal that answer now. I got 64.54 milligrams per liter for the plasma concentration immediately after the 10th dose. So that would basically be the Cmax, right? Because it's right after giving it. And that's assuming that, it's already distributed, which is almost instantaneous in an IV dose. So we're assuming that 0 time point, it's already distributed after the dose. How close do you think we are to steady state at this dose? And I'm pretty sure I forgot to mention on, I think it was slide 12, that the general rule of thumb is that if you wait 5 half-lives, you are at steady state because that is over 97% at steady state, or you're over 97% where the average steady state concentration will be. So that means 5 half-lives, you're pretty safe. So that's the kind of crazy magical number that no matter what drug you're using, right, no matter what dose, no matter what frequency, 5 half-lives is always going to be reaching the steady state, right? In anything, any frequency, any dose, like I said, any drug, the answer is 5 half-lives. So it's a pretty crazy thing. You can kind of prove that to yourselves if you looked up multiple different drugs and kind of ran through the equations and see what you get, and then see if you get, based on its half-life, see if you get after 5 half-lives that the concentration is no longer changing. So how close do you think we are to steady state at this dose? Okay, so if the half-life is 13 hours, well, what's 5, right? 5 half-lives, what, that's 50 plus 15, that's 65. Okay, that'd be 65, 5 half-lives would be 65 hours. I said the 10th dose, right? So we're actually way beyond 65 at this point. The first dose is at 0, and then we have 9 more doses. That's 72 hours. Since the very first dose, we got 72 hours since that. So that means we are beyond the 5 half-lives, right? So we should see that we're at steady state, or even, right, we're even past 5 half-lives. So we're pretty much right on top of the steady state. So if we keep, at this point, if we keep giving this every 8 hours, the concentration should still be close to 64.5. And that would be the Cmax concentration. The Cmin will also be consistent, but it'll be lower, and then the average will be the same. The average of the Cmax and the Cmin will stay the same now for every dose, pretty much. So just continuing this problem here, question is, what is the Cmax and the Cmin at steady state? Actually, we already know the Cmax because we calculated that because we said immediately after the 10th dose, what is the plasma concentration? So if we agreed that we are already in the steady state, we agree, right, that so that was immediately after the 10th dose, that should have been the Cmax, that one that we already calculated. Now, the Cmin, the only difference is the Cmin is just going to be immediately before the next dose, immediately before it. So basically, you use the same equation, and we could use the same n, right? We'll still say after the 10th dose, but we're going to have to use a different time in this case. So think about why that's true. Obviously, because, right, the Cmax is right after the 10th dose, the Cmin is right before the 11th dose. Okay, but you could choose anything, well beyond 5 half-lives and get a good answer. Okay, so if you did like 10 half-lives, for example, that would be very safe. So go ahead and see what you get for the Cmin. Remember, the time that you're going to choose when using the equation to calculate the Cmin, the time after the 10th dose, if you decide to use a 10th dose, it's up to you, but the time after that will be essentially almost time for the next dose, basically. So that time after that will be almost time for the next dose. So what I came up with was 65.46 Cmax. Cmin would be 43.27. Okay. So hopefully that makes sense how we did that. Again, just using the same exact equation. By the way, I think I forgot to mention on the last slide, you could have chosen, for example, 7.999 hours or something like that, and that would have been, you're still using basically that you can use a 10th dose. It doesn't matter as long as you put the correct information in. You could put the 11th dose, 12th dose, but it's got to be at least after 5 half-lives. And then you'd put the time after that dose would be about 7.999 hours, or basically right before the next dose, and you should get that Cmin that I got. Just a kind of theoretical question here. What can we do to decrease the Cmax while keeping the same average steady state concentration. So is there anything we can do in a patient, and actually I already talked about this, this is kind of a review. What can we do to make sure that the patient doesn't see really high peak concentrations with repeated dosing? Obviously with IV infusion that won't happen, but if we gave repeat, really any repeat dosing, it could be oral, but repeat IV bolus, how can we avoid a high Cmax? Okay, so think about that for a second. So pause it right now and think, and then when you're ready, go ahead and play it again. I'm going to give the answer now. So one of the main, well, really the only real good way to avoid a high Cmax is to give a more frequent dosing. So you have a more frequent dosing interval. So instead of every 8 hours, go every 4 hours or every 2 hours. Or again, like I said, the extreme would be like an IV infusion. That way you won't have an up and down spike. You'll just have a very, very steady level. More important, again, for a narrow therapeutic window drug. And that's why I said here, increase the dosing frequency and decrease. Oh yeah, and I didn't mention that you still have to decrease the dose, right? If you're giving it more often, you would decrease the dose proportionately to achieve about the same steady state concentration. Now for IV infusion, we're actually kind of lucky because the equation's a lot easier. Okay, and the one thing that's kind of different here that you haven't seen is the R, or the infusion rate, and that has to be entered in milligrams per hour units, and the T or time must always use the same units. In this case it'll be hours. Okay, so keep in mind, there might be a scenario where you're not given it in milligrams per hour. You might be given, for example, the concentration of drug in the infusion and then the milliliters per minute, right? So you have to figure out, it's not that difficult, right? But to figure out that how many milligrams per hour would that be. Okay, so I want you to do that on your own. So again, with this number of milliliters per minute, this number of milligrams per milliliter, how many milligrams per hour would that translate to or be converted to? Okay, and that's what you would enter for the R value. Okay, so given this drug data here, I want you to figure out what the steady state concentration would be with an IV infusion. Okay, so everything else pretty much standard volume distribution. You have to get the KEL from the half-life, and I showed you how to do that. Okay, so please use that equation as well. Otherwise, pretty much just plugging it in and calculating that. So go ahead and pause it. I'll give you 5 seconds and then I'll continue. So what I came up with was 155.8 milligrams per liter at steady state, and I knew it was liters because our volume of distribution is in liters, and I knew it was milligrams because our R value is in milligrams per hour, but it's milligrams as the mass unit. So that's going to be milligrams per liter. So one more time I wanted to revisit the units and talk about what rules there are. Really the primary rule is that we need to stick to the same units within an equation. As long as the units within the equation are consistent, we should be okay. So for example, if time or T is in hours, KEL must be per hour. And then the infusion rate must be some mass per hour, right? And I'm not gonna try to confuse the heck out of you with that. I'm gonna try to be as consistent as possible. But again, if I do ask you about converting the infusion rate to that R, that's the only thing I want you to really get familiar with. For the infusion calculations, how do you convert that infusion rate to an actual mass per hour? The plasma concentration, so your final number, will always be in the units that you use for the dose over the units that you use for the volume of distribution, as I mentioned. So please keep those rules in mind. The reason why I don't want to hold you responsible for the calculation for multiple oral doses, although that's the most common scenario that we see, is because of how complicated the calculation is. And I apologize, it's a little pixelated. I copied this from a text and I just changed the K to KEL to make it more clear. But this is how you would do it. You're still using the same constants. You're still using tau. You're still using the nth dose that you're interested in and everything in the time, but it's just a lot more complicated because now you have the absorption kinetics. So don't worry about that too much. I just want you to know that that can easily be done and it exists. So finally, I want to talk about loading dose. Remember that it takes about 5 half-lives to reach steady state. Okay. What if we wanted to accelerate the achievement of steady state? The answer to that is giving something called a loading dose. A loading dose is very intuitive, right? It means we're going to give a higher dose just for the first dose, and then from that point on, we're going to give a consistent and lower dose, right? So we'll start off with something high, and then we'll go consistent and lower than the original dose. And it's really hard to get exactly at steady state with the loading dose, but you can get much closer to steady state with the loading dose. And this is the equation. Okay, I'm not going to test you on this equation. I'm not going to have you use it. I think that's more clinical anyway, so I'll, hopefully we'll reserve that, and you might see that again. But basically, I'm not going to ask you that on the test. So in this case, the DL is the loading dose. The C infinity sub AV is the desired concentration at steady state. F is the fraction absorbed, which is 0 to 1. And S is the fraction of the formulation that is active ingredient. And that could be very confusing, but what it means is if you give someone 100 milligrams, you want to make sure that you're not saying 100 milligrams. For example, if it were metoprolol tartrate or the salt, you don't want that salt included in that calculation. You just want the actual active ingredient. So that would be the mass of the active ingredient, would really be the S. And that's why I don't really want to get into that. I don't want to require you to know that equation at this point because of some of the nuances like that. So what do different loading dose to maintenance dose ratios look like on a graph? Okay, obviously if your loading dose is too high, you'll overshoot, and it'll take still a while to get to steady state. If you're really good at it, you'll almost be at steady state on the first loading dose, which would be this example B here. D would be like, if you're on D, that would basically be probably just your normal dose and you never really gave a loading dose. Okay, so interestingly, no matter what your loading dose is, if subsequent doses are all the same as each other, right, you will eventually reach the same steady state regardless. And it's still, well, it'll be about 5 half-lives if you overshoot or you don't have a loading dose at all, it'll still be about 5 half-lives. But you can get close, like I said, you can get closer to the steady state if you have a really good loading dose and you do it correctly. This concludes the lecture on multi-dose regimens in IV infusion. We're getting pretty close to the end of the material. The next few things will be related to clearance and bioavailability and things like that, and then we'll pretty much wrap it up with the basic pharmacokinetics of the course.